Good afternoon, everybody. This is Orekoya Olusegun Physics Mathematics Fundamentals on YouTube. Today, we are taking a topic in mathematics, and that topic is on matrices. That's the plural form of matrices. The singular form of it is matrix. Now, it is assumed that you understand the algebraic operation on matrices, such as addition, subtraction, multiplication, and division. So, if you do not have this background, please, you are kindly advised to do so, because today we want to take a topic under matrices, and that topic is about Eigenvalues, values, and vector. The first one is called Eigenvalues. The second one is called Eigenvector. So now, before we can get these values, we should understand what a vector equation is. Vector equation: ax is equal to b. So this A is the matrix of the coefficients of a system of linear equation, while this particular x stands for the matrices of the variable, and this b is the matrices of the constant. In my further explanation, you will understand what I mean by that. Now, if this particular constant matrix, this b, if it is equal to 0, then we have what is called ax is equal to 0. This type of equation is called homogeneous equation. But if this b is not equal to 0, that is, we have equation of ax is equal to b, then that equation is called non-homogeneous. Take note of that. Now, for the eigenvalues and vectors, this equation for the eigenvalues and eigenvectors work with this particular format. Ax is equal to, instead of a here, you put a scalar value called the eigenvalue, then with the variable vector matrix here. So the next thing we do is to equate everything to matrix 0 by carrying this one to this other side of the equation. So we have ax is equal to as minus this particular scalar value, that is called Eigen's value. Then with this x, everything will be equated to 0 vector. So we can factorize this variable vector out here. Then we are left with a minus this scalar value, then multiplying this variable matrix matrix. So you equate everything to 0. Now, because this particular scalar is ordinary number, which is not a matrix, we can convert it to matrix by introducing the identity matrix I to it. So we have a minus this scalar value, which is an eigenvalue, then times identity matrix. We say multiplying this vector is equal to 0. In a nutshell, this particular a, which stands for the matrix of the coefficients, can be for matrix of order 2 by 2, that is I'm talking about square matrices, or it can also stand for order 3 by 3 matrices, and so on and so forth. So this particular order of matrix will determine the order of the identity matrix we are going to introduce. So that is that for that. Now, let's work out a problem here. The question says, if we are given matrix A to be 4 1 then 3 2. We are talking about first column, first column 4 3, second column 1 2, first row 4 1, second row 3 2. We are given this vector, this matrix, and we are asked to find the eigenvalue lambda. Then if you look at this equation that we have here, this particular x stands for eigenvector, while this lambda stands for eigenvalue. So the second question says we should find eigenvector 2. So what we are going to do is to convert this particular matrix into this equation format. So our A, that is a matrix A, is already this, so we put it inside this expression. So we are going to have something like 4 1 3 2. Then this bracket, write it like this, then minus this eigen value, then times the matrix, this identity matrix I. The identity matrix I is 42 by 2, which is 1 0 0 1. If you are wondering how I happen to come about this, for 2 by 2 matrix, we have two rows. You can write rows like this, horizontal line 1 2. Then we have the column. We can write this vertical line 1 2. So where these lines intersect for the identity matrix, this particular matrix, we can draw a diagonal line like this here. The entry or the element that stand on this diagonal is always 1 1, while the under the diagonal, the entry will be 0. On top of the diagonal, the other entry will be 0 there. So by the time you bring what I have here out, you have 1 0 0 1. That's how I got this I in this equation here like this. Then this vector x can be written as x1 x2, which is the eigenvector. Then this eigenvector is multiplying this particular vector here. Then we equate them to 0. So that 0 actually means column vector OO, like that. So then the next thing we are going to do to find the eigenvalue, this that we have here, is that we find the determinant of this vector that is here. The determinant. So you put the determinant sign here to show that you want to find the determinant. So we have the determinants of this content. And now, how do we get this content out? This actually means this scalar quantity, which is a eigenvalue, we multiply each of these entry inside. So this vector is still as it is. So I write it as a 4 1 3 2. Then this minus this, you can not say plus, now say minus this times each of these entry. So we are having minus lambda, then minus lambda times 0 will give us 0. Minus lambda times 0 will give us 0. Minus lambda times 1 will give us minus lambda. Then we equate the determinant to 0. So we still put the determinant sign here as it is. Then what we are having here now is that we are going to add this quantity together. So when we add it together, 4 plus minus lambda will give us 4 minus lambda. Then this 1 plus 0 will still give us 1. And 3 plus 0 will give us 3. 2 minus lambda will give us 2 minus lambda. So we are going to find the determinant of this expression, we equate it to 0. So we need to find the determinant of that particular expression. So and you remember how we normally find the determinant right from time. For instance, to find the determinant, let's say we have this a, b, c, d. To find the determinant, multiply along this first diagonal, which is also known as the principal or the leading diagonal. That is AD. You now subtract the second diagonal, the product of the entry along this leading diagonal, which is AD, A times Z, minus the product of the entry along this second diagonal, that is CB. That's how to find determinant. So we are going to use that idea for this one now. We multiply along this diagonal here, then like this. So when we multiply 4 minus alpha times 4 minus alpha times 2 minus minus lambda, because when you multiply 2 times minus lambda is 2 minus lambda. So we have something like this product written out. We have 4 minus lambda times, we multiply 2 minus lambda. Then we now say minus, we multiply along this diagonal. That's 3 times 1. We give us 3. We equate it to 0. Now, when we open this bracket, we use 4 to multiply 2. We use 4 to multiply minus lambda. We use this minus lambda to multiply 2. We use minus lambda to multiply minus lambda. So we are going to have something like 8 minus 4 lambda minus 2 lambda plus alpha square minus 3, lambda square minus 3 is equal to 0. Now, we can see that we are arriving at something like a polynomial function, which is a quadratic equation in this particular case. So when we add the like terms to this lambda square, we can put it in the front. So when we add all these quantity together, we have minus 6 lambda plus 5 is equal to 0. So this is more or less a quadratic equation. So we need to factorize this quadratic equation. We think about two numbers that we multiply together to give us plus 5, and that we add them together, the same number a plus b. Any two numbers that we add together to give us minus 6, we multiply together to give us a plus 5. We know that it's going to be minus 5 and 1. So instead of writing minus 6 lambda, we're going to write it as lambda square minus 5 lambda minus lambda plus 5 is equal to 0. So we factorize the lambda out here. You have lambda bracket lambda minus 5. Here too, we factorize it out, lambda minus 5, this minus lambda outside. We say is equal to 0. So in a nutshell, we are going to have this one was supposed to be 1. So we are going to have lambda minus 1 times lambda minus 5 is equal to 0. So in a nutshell, when each of these is equal to 0, that means if each of these factors is equal to 0, that means the product of these factors will be 0. In a nutshell, our lambda will be 1 when we carry this minus 1 to this side, and our lambda 1 is 1, and lambda 2 will be equal to 5. So these are the eigenvalues that we have for this particular question that we are given. We already solved question case number 1. So to solve case number 2 now, what we are going to do now is to consider when our lambda is 1 and when our lambda is 5. So we go back to the original vector equation that we have. So when our lambda 1 is equal to 1, we substitute into this particular original equation that we have here. This particular equation that we have here, when our lambda is 1. So 1 times this identity matrix will give us this identity matrix. So with the original matrix A that we have here before. So we are going to have something like this now. We know we have this matrix of the coefficients minus identity matrix, then times this eigenvector x is equal to 0. By substituting these coefficients, that is the original matrix that we are given in the equation, which is 4, 1, 3, 2. We substitute to this a, then minus the identity matrix for the 2 by 2 will be 1, 0, 0, 1, then everything times this eigenvector, and that eigenvector actually is x1, x2, then this particular 0 is 0 vector, which is 0, 0 that we have here. So now we subtract the entries in this particular vector from this entry by subtracting corresponding entry from each other. So it's like saying 4 take away 1, that will give us a 3. 1 take away 0, that will give us a 1. 3 take away 0 give us 3. 2 take away 1 give us a 1. So we are going to have this particular vector for the whole of this one now, then times the eigenvector here, then is equal to this 0 vector. So what we have here is that we are going to multiply this vector, the row of this vector times the column of the second vector. So we say 3 times x1, that will give us 3x1 plus 1 times x2, that will give us x2. Then we say is equal to 0 for the first row here. You can see that what we have here as the first row is what we have here as the second row. So the same thing, if you use this 3 and 1 to multiply this column vector, we have 3 times s1, that's 3s1 again, plus 1 times x2, that gives us s2 is equal to 0. So we have the same similar equation when we use row 1 and row 2 to multiply this. Each of them will be equal to each of these 0. So in this case now, we can write that our x2 is equal to minus 3x1. So I believe that you got the expression I have here. Now this particular vector that I have here is actually vector x, which is x1, x2. So when we substitute what we have here, this is x1 still remains as s1. So instead of this x2 here, substitute minus 3s1. We have minus 3x1 there. So we can factorize s1 out in this column vector. So we are going to have something like s1 bracket 1 minus 3. So what we have here now is 1 minus 3. So the eigenvectors now, eigenvectors that we have, eigenvectors that we have now, the first one that we got was 1, 1. The first eigenvector that we got was 1, 1. So this other one that we have here is 1 and minus 3. So like I said, the first eigenvectors that we got here, the eigenvalues that we have here is lambda 1 and this one is lambda 2. So here now I've gotten the eigenvector for this particular matrix. So I believe that you have learned one or two things on what we've done so far. I want to say a big thank you. Have a nice day. Bye.